Hello. In this video, we're going to take a look at Skills Practice 18.1, the speed of light. Please remember to pause or rewind the tutorial as necessary. Let's begin. The speed of light is a fundamental quantity in physics. Light is an electromagnetic wave. Waves are characterized by their frequency and wavelength. In this skill sheet, we will work with the formula that relates the speed of light to the frequency and wavelength of light. Part 1. The speed of light is related to frequency f and wavelength lambda in the formula below. Frequency is given in hertz, or cycles per second, and wavelength is given in meters. The speed of light in a vacuum is 3 times 10 to the 8 meters per second. So you'll notice that this equation is very similar to V equals frequency times wavelength. The only thing we're doing is we are replacing C with the speed of light. And it has this value right here, 3 times 10 to the 8 meters per second. Different colors of light that we see correspond to different frequencies. The frequency of red light is higher than the frequency of blue light. Their speed is, however, the same and equal to C, the speed of light. Therefore, the wavelength of red light is higher than the wavelength of blue light. When we know the frequency of light, the wavelength is given by lambda is equal to C over frequency. We get that by solving this equation right here. So if we take C is equal to frequency times wavelength, and we solve for lambda, you have to divide by frequency. And you can see it's C divided by frequency. Similarly, if we take our equation, C is equal to frequency times wavelength, but this time we solve for frequency, this time we have to divide by lambda. And you can see it's going to be C over lambda is the frequency. Now, let's take a look at the color spectrum so we can make some sense out of higher and lower frequencies. Over to the side, let's write this down. The wavelengths of light in the color spectrum are red, orange, yellow, green, blue, and violet. Well, the reddish colors have smaller frequencies, but they have larger wavelengths. Blue-violet has much smaller wavelengths. The wavelength's going to decrease. Lambda decreases, right, as we go from red to violet. And we have much larger frequencies. So you can see that the frequency is increasing as we go from red to violet. And again, why is that? Because the speed of light is constant. So if the speed of light is constant, you can see that smaller frequencies of red color would correspond to larger wavelengths. Similarly, smaller wavelengths of violet color would correspond to larger frequencies. Number 1, yellow has a longer wavelength than green. Which color has the higher frequency? Well, the highest frequency, higher frequencies go with shorter wavelengths. Well, we're told that green light has the shorter wavelength than yellow does. So this would be green light. Green light has a lower frequency than blue light. Which one has the longer wavelength? Okay, longer wavelengths go with smaller frequencies. We are told that green has a smaller frequency than blue. So again, our answer is referring to green light. Green light is going to have the longer wavelength than blue. Now, question 3, 4, 5 can be answered in the tables below. For question 3, we are given the frequency, and we are looking for lambda. Number 5, we are looking for frequency, and we are given lambda. Finally, number 5, we are given lambda, and we are given the frequency, and we're trying to find lambda. So number 3, we're looking for lambda. We're given 2 things. We're given the speed of light in a vacuum, which is 3 times 10 to the 8 meters per second. You're also given the frequency in number 3 at 750 times 10 to the 12 hertz. Okay, we'll finish the problem in just a second. Number 4, you are looking for frequency. We are given the speed of light. Speed of light is a constant value. And you are given lambda, the wavelength. The wavelength in number 4 is 580 times 10 to the negative 9 meters. Okay, and finally, number 5, we're looking for wavelength, for lambda. You're given the speed of a wave of light, 3 times 10 to the 8 meters per second. And we're given the frequency of 460 times 10 to the 12. Okay, now the equation we're going to use in each case is C equals F lambda. So I'm going to copy this down 3 times. Okay, and let's solve each of these problems for their respective unknown. So C is equal to F lambda. You are looking for lambda, so you need to achieve that by dividing away the frequency. So lambda is equal to C divided by the frequency, which would be 3 times 10 to the 8 over 750 times 10 to the 12. Okay, let's go put this in our calculator. We're going to go 3 times 10 to the 8 divided by 750 times 10 to the negative 12, or times 10 to the positive 12, divided by 750 times 10 to the 12. Okay, very small wavelength. Now, notice, in order to put this in proper scientific notation, I have a decimal point, 6 zeros, and a 4. So I get this answer, 0.0000004 meters. Well, in proper scientific notation, I'd have to move that decimal over 1, 2, 3, 4, 5, 6, 7. So it's 4 times 10 to the negative 7 meters. Number 5, we're going to take that equation. C is equal to F lambda. This time we're solving for F. We can achieve that by dividing away the lambda, dividing away the wavelength. So frequency is equal to the speed of light divided by the wavelength. We're going to go 3 times 10 to the 8 meters per second over 580 times 10 to the negative 9 meters. Okay, let's try putting that in our calculator. Okay, so we have 3 times 10 to the 8 divided by 580 times 10 to the negative 9. And we get about 5.17 or 5.2 if you want to round it up, times 10, E14 means times 10 to the 14. So 5.17 times 10 to the 14 hertz. Finally, number 5, we're going to take that equation, C equals frequency times wavelength, and we're going to solve for wavelength this time. So we're going to divide away the frequency. Wavelength is equal to the speed of light divided by the frequency. So 3 times 10 to the 8 meters per second divided by the frequency of 460 times 10 to the 12 hertz. Three times 10 to the 8 divided by 460 times 10 to the 12. Very small number. What we have is a decimal point, 6 zeros, and 652. We don't need those other digits. So we are 0.000000652 meters. And I would fix that by moving the decimal 1, 2, 3, 4, 5, 6, 7 times to get the decimal after the 6. And in proper scientific notation, that would be 6.52 times 10 to the -7 meters.